Welcome. Today we're going to talk about absolute value transformations. And what I'm hoping is that we refresh your memory on what absolute value functions are, and we make connections between absolute value functions and the functions that you studied in Group 1, linear and quadratic functions. We're going to talk about their names and their ranges and just general ideas for how we can manipulate these cool functions. All right, let's get started. The first thing I'd love for us to do is just remember what the absolute value of a number is. And technically, this is the distance. I should write this down, shouldn't I? It will be the absolute value of any number is technically the distance from 0 on a number line. I'm tempted to put a hashtag there, but let's be formal here. So it's the distance from 0 on a number line. And since distance is actually not a net, you can't have a negative distance. Think about it, you can walk backwards, you can walk forwards, but in all cases you're burning calories. So you can't really have a non-negative absolute value, or distance. So that's why we have an absolute value, because sometimes we need to measure things and they just can't be negative. We have a special symbol that we use for any function or for any absolute value. We put these vertical bars around a number or a function, and that indicates to us that we are taking the absolute value of whatever the inside of the absolute value bars evaluates to. And folks, the absolute value bars, those act as grouping symbols. So much like you use parentheses and brackets and you follow order of operations, the absolute value bars are also grouping symbols. So if you're asked to simplify, you would simplify inside the absolute value functions differently than you would necessarily things that lie outside the absolute value. You don't do it differently, but they act as grouping symbols. And that's important when we do solving equations later on. This is the technical verbiage. It says that if you take the absolute value of A, where B is is greater than 0, or the absolute value of A will be some positive number B. So A is either equal to B or it's equal to negative B. It basically means that if I took the absolute value of X, then I get, let's not even make it X, let's make it 8. Absolute value of 8 is going to be 8, and the absolute value of a negative 8 is also going to be 8. So there's just an example of what this would look like. The absolute value function is a cool kind of function because it doesn't matter what your X value is, the output will always, or the Y value will always be a positive number. Then you get this really cool parent function that looks similar, has some characteristics it shares with the quadratic function. It has a vertex, but they're two linear equations sort of melded together. So this is what an absolute value parent function would look like. It is V-shaped. The domain is going to be all real numbers. The range for the parent function is everything greater than 0. And you'll notice they're using interval notation here, which I love. You don't have to put positive infinity, but you can if you'd like to. It has an x-intercept and a y-intercept. Both of those for the parent function happen to be at 0, 0. We all know that parents are boring, so that's not a real surprise. And f of x less than 0, there's really not going to be one of those. So that is some verbiage about the absolute value function and what its graph looks like. The easiest thing to do, folks, is if you're trying to make a graph of a function that is for an absolute value function, make a t-chart, make a table, or use your calculator and put it in the y equals portion of your calculator. Pull up Desmos and use Desmos to come up with a table of values, and then just connect those points. Remember last time we talked about transformations of absolute value functions and all sorts of different kinds of functions. So you'll just hopefully remember this. The A represents a vertical stretch or compression. The B represents a horizontal stretch or compression. H is the translation left or right in a horizontal direction, and K represents my vertical translation up or down in this case. So let's just go through the exercise of creating the parent function the parent function graph and a table for the parent function. It's pretty trivial to do. It's not just uber complicated. I'm going to skip a few numbers just to get a better graph and not everything's so crunched in. I'm just going to look at a few X values. You can use any X values you want within reason because my graph only has 6 units up or down, left or right. So if I determine that these are going to be my X values, then when I take the absolute value of those, remembering that my absolute value, what I'm doing is I'm just taking the distance from 0 to -4, and in that case, it's going to be 4 units. The distance from 0 to -2 is 2 units. So you could just think of it as the sign goes away. It always becomes positive. So these are ordered pairs, and I can actually graph those ordered pairs. My vertex is at 0, 0. Well, I'm going to call him out. That is also going to be, as we said before, the x-intercept and the y-intercept. My other points are 2, 2, and 4, 4. It does have a line of symmetry. It is symmetric, which is kind of handy. Please excuse my crooked lines here. Graphing is not really my forte, but there we have it. We have made a t-chart, a table, and we have graphed those ordered pairs to come up with the absolute value parent function. And then anything I do from here, the adding and subtracting to the end of it, inside of it, multiplying the X values inside the absolute value symbols by a number or even outside, all of those are going to be the different transformations that we talked about last class. When I am looking at the domain and range for the absolute value function, I'm going to first remember that my domain are my X values and my range are my Y values. If I'm using inequality notation, as we said up above, the domain is going to be in all real numbers. So you could do it, let me just think, I'm going to be formal. -infinity, less than X, less than infinity. That's using my inequality notation. To use interval notation, which is my preference, I'm going to do -infinity to infinity. I'm going to use parentheses here because I can't actually touch infinity. They translate to the same thing as a less than sign as opposed to a less than or equal to. And if I'm using set builder notation, this is some strange stuff. Y'all are all familiar with it because you've seen it in Algebra 2. The thing is it doesn't need a whole lot of direct instruction because it's pretty weird looking, but y'all are so good at this that you get the point. The bracket is set builder notation, and then we always put the variable we're concerned about, and in this case, domain are our X values. Then I put this vertical line, and the way I read this would be X such that X is an element of all real numbers. And then I close my brackets. So this weird E, it's a Greek E, that's element of. Yes, and this bar right here, the vertical bar, means such that. So those are some kind of funky notations that we use when we're using set builder. Just some rules of set builder. If I look at the range, as we said up above, because my vertex is at 0, 0, I change directions. My Y values never enter a negative range. So 0 is actually my lowest Y value. And I do actually touch it. So my Y values are going to be less than or equal to 0. And I'm going to go up forever. So I would say that the Y values have to be less than infinity. So just if you remember, I use greater than or less than for anything that has arrows. Yes. And then sometimes you can use an open dot as well. We don't do that as much in Algebra 2. And if I have a less than or equal to, greater than or equal to, I'm going to put a comma between those, then that would be if I have a specific endpoint where it's solid or perhaps it just stops. Okay, so that's the inequality notation for the range, and that you're welcome to use that if you would like to. I like set build or notation. I am touching a 0. That is the lower bound of my range. I'm going to put the 0. I'm going to put a bracket because that means that I actually touch it. And then I go up forever so I use the infinity symbol, and I can't touch infinity, so I use a parenthesis. I'm doing set builder, it's similar. I still use my bracket. This time I'm talking about y values because this is range. So I'm looking at the y's such that, and here you could do it a couple of different ways. I would say y is greater than or equal to 0, and I think that covers it. You could also put this entire inequality statement here inside the set builder notation if you would like to. This tends to be a little bit more concise. So that is the parent function, y'all. And as promised, it's about as boring as you can get. All right, so let's look at some examples of absolute value functions. The first thing we're going to do here is we're going to graph this new function f of x equals absolute value of x plus 2. So I immediately want to identify what transformations have taken place in this function. I notice that this plus 2 happens outside of the grouping symbol, the absolute value symbol. So I know it's vertical. And because it's being added or subtracted, I know that this is going to be a translation up 2. And I remember that from our lesson last class. So if I think about what does that do to my parent function has x and y values that we said on the previous page. Take the x values and just make them positive. So those are my parent functions, and I'm going to just real super quick, and I apologize for not having done this ahead of time. I'm going to just sketch the parent function in so we can see what the transformation is. All right, so that's my parent function. And we learned that when I do a vertical translation up to, what I'm doing is I am going to add 2 to all of my y values. My x values do not change, but I'm going to add 2 to my y values. So instead of a 4, it's going to be 4 plus 2, or 6. Instead of a 2, I'm going to add 2, and that becomes 4. 0 plus 2 is 2, 2 plus 2 is 4, and 4 plus 2 is 6. So these are my new ordered pairs for the function f of x plus 2, or absolute value of x plus 2, however you would like to think about it. And now I just need to plot these points. So I'm going to go over -4 up 6, over 2 up 4. And you'll see that as it's consistent with what we discussed last class, this transformation does not change the shape of my graph. It just slides it along the coordinate grid, moving it up 2 spaces. I note that I still am going in the direction of infinity for my domain. So my domain is still going to be -infinity to infinity. A vertical translation will not change my domain values, but it has changed my range values, because you'll notice instead of having a vertex at 0, 0, now the lowest point on my graph, if you use the box test, if you use, draw your box around your graph, the lowest point is at +2. So now the vertex becomes my range limit. That is the lowest point on my graph, and I continue upward forever. So that's my range statement, and that is different from the parent function's range statement. Let's look at another one. This is just so exciting. I went ahead and again drew out the table, but I neglected to sketch my parent function, which I like doing because I think it just gives me a reference point. So there's my parent function. All right, so in this particular function, I'm looking at the absolute value of x minus 3. And the first thing I note is that this is all happening inside the grouping symbol. So this is a horizontal, because inside it happens in horizontal happens inside. It's inside my absolute value bars. And I remember that horizontal or insiders lie. So instead of going -3 to the left, I'm actually going to shift this to the right 3. So it's a horizontal translation, right 3. I'm running out of room there. No one will ever accuse me of being methodically neat here. My parent function, we are hopefully becoming quick with identifying what my parent function values are. To find the ordered pairs that will allow me to graph this translated function, I'm going to remember that horizontal transformations change my x values. and my y values will stay the same. So here, I'm moving to the right 3. I'm doing the opposite of what I see here. So I'm going to add 3 to my x values. I'm remembering that the y values will stay the same, but now my x values are changing. -4 plus 3 is -1. -2 plus 3 is 1. 0 plus 3 is 3. 2 plus 3 is 5. Just check me, make sure I don't screw this up. All right, so that was easy enough to do. And now I have a new table of ordered pairs that I can graph. And hopefully what I notice when I graph this is that my graph has, in fact, not changed its overall shape, but instead, 1, 2 has just, there's 2, has just changed where it is along the x-axis. I have to stop talking for a moment. I can't talk and graph at the same time. Okay, so I think our new function is going to look, crooked line, something like that. And you'll notice that as we predicted, the graph has just moved to the right 3 spaces. Even though it's a horizontal transformation and horizontal changes the x values, I still am going to infinity in both directions. So I'm going to say -infinity to infinity. If you like it, you could say that x is, if you use set builder, x is an element, or x such that x is an element of all real numbers. If you want to just go crazy and try something different. For my range, you'll notice my vertex has not moved vertically up or down. So my range actually has not changed. I still have a vertex at 0. That is the lowest y value that occurs in my graph. And I'm going up forever. You could do inequality notation and say that y's have to be greater than or equal to 0. Okay, so those were just translations, up or down, left or right. I'm going to grab hold of this paper any moment now. Let's look at another one and see what this looks like. In example C, we notice that there is, it's an absolute value function again, but now I have a negative in front of it. So what I'm essentially doing is multiplying all the y values of this function by -1. That makes this a vertical because it's outside, and it's a reflection. It's a vertical reflection, and because it's vertical, it's over the x-axis. So I'm going to flip over the x-axis. I have my parent function, 42024, feels like a phone number back in the day when people actually memorized those. And if I sketch in my parent function with crooked lines, because why not? Then my parent function looks something like that. As I reflect, I'm going to change my y values because it's vertical. And I'm going to multiply everything by -1. So instead of having a +4, I now have a -4, a -2, 0, -2, -4. And my graph should have the same shape because I have not stretched or compressed it, but instead I have reflected it over the x-axis. And this does some interesting things to our range. So be careful when we do our range. The domain did not change. It's still -infinity to infinity. Or if you want to, you can do -infinity is less than x, less than infinity. But when I'm doing my range, I need to be super careful because note, now my vertex is the highest point on my graph. Reflections change where my vertex lies in my range statement. So now 0 is the highest point on my graph, and my graph goes down to -infinity. This is something my students flip all the time. They tell me that this range statement is really 0 to -infinity. And so they have identified the parts correctly, but -infinity is smaller than 0. So he always goes on the left. All right, one last example for this. Let's look at the function f of x equals 2x. And when I look at this function, the first thing I note is that my x values are being multiplied by 2, and that this is inside the grouping symbols. So this is actually a horizontal. It's going to be the opposite of what I expect. If I am multiplying everything by 2, then I am actually compressing it. Okay. So this is a horizontal compression. And we talked last class about how what I'm really doing is I'm doing the opposite. So instead of multiplying by 2, I'm actually multiplying my x values by 1/2. And it's really 1 over 1, it's 1 over 2. So that's important to remember. I can talk 4, 2, 0, 2, 4. That is my parent function. My range values or my y value do not change because this is a horizontal compression, and horizontal changes my x values. And so maybe I purposely chose numbers that were even so that when I could take a half of them, they would come out to be whole numbers. Half of -4 is -2. Half of -2 is -1. Half of 0 is 0, 1, and 2. So now I have new ordered pairs that I can graph. If I were really being prepared, I would go ahead and graph my parent function. And now I can graph the ordered pairs represented by this new function, absolute value of 2x, -2 up 4, -1 up 2. My vertex is the same. My horizontal compression did not change my vertex, which means it's probably not going to change my range statement. I don't want to make absolute value or absolute statements, but that is a suspect. And here's my new function. So it did, in fact, compress in a horizontal direction, did not change my domain values. I'm still going to go in the negative direction infinitely and in a positive direction infinitely along the x-axis. And my range value has not changed because my vertex is still 0, 0. So I'm still going to 0 and go up forever. So there you go, guys. We have some practice now with graphing absolute value transformations by looking at what the transformation does to individual ordered pairs. All right, 2 more examples and then we will be done for this lesson. I notice in both of these examples, we are doing multiple transformations. So what I went ahead and did is I finally graphed the parent function before I got started, and I went ahead and made a table of my parent function, just some random values for it. And what I'm going to do is I'm going to use my order of transformations, the Harry Styles rocks V-necks, horizontal translations, vertical stretches or compressions, horizontal stretches or compressions, reflections, and vertical translations. I'm going to use that order, and I'm going to do one translation at a time to come up with some ordered pairs that I can use to graph this function. This may seem like overkill because perhaps you would look at this and say, oh, I go left 1 and up 2, and you can sort of do it from sight. But when you have multiple transformations and those include vertical stretches and compressions, that can be kind of tricky sometimes. And as always, the order that you do these transformations definitely matters. So let's jump in. The first thing I notice is that in this example, I have to look for my horizontal translations first, and there is a horizontal translation. Insiders lie. So this is going to be going in a negative direction or left 1. So what I'm going to do is I'm going to take my x values and I'm going to subtract 1 from each of them. I'm going to remember that my y values are not going to change, but my x values will. So if I just subtract 1, becoming more negative, hopefully I'm going to get these right. And now I have a new set of ordered pairs that I can graph. Now note, I can graph these. This is not my final graph. This is not my end result because I've only done one transformation. If you'd like, you can go ahead and graph this and ensure that it really has, in fact, moved one spot. Or you can go ahead and do the second transformation first and then just graph the final result. Either one works. I'm going to cheat a little bit and use a piece of paper to make a straight line. So I'm going to still make this a dashed line. It's a slightly different color, but this helps me see that this is not my final graph. This is just a step along the way, right? Okay, so that was my horizontal translation left, but I'm still left with a vertical translation. There is no stretch compression because my X value is not being multiplied either horizontally or vertically by any constant. So I don't have to worry about stretches or compressions. There is no negative in front of the X inside of my absolute value symbol outside. So there are no reflections, leaving just a vertical translation up to. For this one, I'm going to remember that my Y values are changing because it's vertical. So I'm going to add 2 to all my Y values. So they become 6, 4, 2, 4, 6. And this time, my X values do not change. -3, -1, 1, and 3. And now I finally have the ordered pairs that represent the final graph, or the graph that I was actually asked to make, the function X, absolute value of X plus 1 plus 2. And when I graph this, I'm going to go over -5 and up 6. Wow, those are such small little numbers. What are the odds that I do this correctly? They're pretty slim. I notice my vertex is at -1, 2, so I'm going to go ahead and draw that in, and I'm just going to make a straight line and assume that I can connect points in a meaningful way. The pressure. Okay, so that should be my new function f of x. And that is a way, folks, to graph a function that has multiple transformations occurring on it. And this will work not only with absolute value functions, but this technique works with any kind of function that you might be interested in graphing. Let's do one more. In this particular case, I am again going to look for horizontal translations, and there is one. This one is subtracting 4 from the X values. Since we know insiders lie in a horizontal direction, this is going to be going to the right 4. I know that that means I'm going to add 4 to my X values. When I do that, -4 plus 4 is 0, -2 plus 4 is 2, 4, 6, 8. Is that right? 4 plus, yeah, that looks right. I know when I'm doing a horizontal translation, my X values do not change. So I'm just going to record those as is. I'm going to look for a stretch or compression. There is nothing being multiplied by X either inside the absolute value or outside the absolute value. So there are no stretches or compressions. There is no reflection. The last component that I see is the vertical translation. And in this case, that's going to be down 5. Sorry if it's so cramped up here, y'all. I just run out of space. Okay, so that means I'm going to subtract 5 from my Y values because it's a vertical translation, giving me -1, -3, -5, -3, -1. And again, my X values do not change because this is a vertical translation. And I am left with some values that represent my new function. I'm going to go ahead and graph those. 0, -1 Palmer, 0, -1. I'm going over 2, down 3, over 4, down 5. Feel like I might have screwed that up. Yes, I did. So many times. Okay, we're just going to go with it. And I know that just do it. You know, I really feel like these numbers are so hard for old people like me to see. -3, right there. And 8, -1. Ha! How do you like them? Who says that? Okay, there's my new fun. Notice it has not changed its shape. It's still up 1 over 1, up 1 over 1. If you want to think of it in terms of slope, hasn't changed its shape because there was no stretch or compression. I've just moved it horizontally and vertically. Folks, that's how we graph transformations of absolute value functions, the vocabulary behind them. If you have any questions, make sure that you come and see me. Otherwise, we'll talk more next.